All right, and we're back for the challenge problems. If you're not particularly interested in these, that's okay. You can stop the video here. Make sure you have the homework due by whatever I said in the remind message. It should be next Wednesday, I believe. Make sure you do the homework by then. If you have any questions about the homework, you can text me on remind, shoot me an email. If you want to do something one-on-one in real time, we can set up a Skype appointment. Don't worry, we can make it happen if that's what you'd like. All right, on to the challenge problems. Number 1. Suppose a fair coin is flipped 10 times and comes up heads each time. Okay, so we know the coin is fair. We flipped it 10 times and it comes up heads each time. So that's really, really strange. But it's possible. What is the probability of this happening? Okay, so we want to know the probability that we get heads 10 times in a row. Well, again, problems that ask you what the probability of a bunch of things happening together start with the probability of each individual thing happening. So what's the probability that the first time that we flip the coin we get heads? The first time, just the first time, it would be 1/2, right? And then what's the probability it's heads the second time? 1/2 again. What's the probability that the first two are both heads? What would we be doing with these 1/2s? Multiply. Multiply. And you can see we want this to happen 10 times. So this is going to be one half times itself 10 times. So this is 1/2 to the 10th power. Let's see, that would be 1 over 2 to the 10th power. That'd be 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024. 1 over 1024. That is approximately 0.1%. I would take either of these as the answer. I actually prefer the fraction because it's exact, but in terms of seeing really how small is this, it usually helps to write it as a percentage. Okay, so only about 1 in 1,000-ish, okay, 0.1% of the time would this happen. Not super likely. That's why you don't really get 10 heads in a row very often. It's not a very common occurrence. Okay? But what is the probability of the next flip being tails? Given that this happened the last 10 flips you had. Does the coin remember that the last 10 flips were heads? No, of course not. The coin doesn't have a brain. The coin doesn't know anything. What's the probability that your next flip is tails no matter what happened in the past? It's 1/2. Okay? Lots of people lose a lot of money gambling because they don't understand this. They would see somebody maybe playing a game where they flipped 10 coins in a row and they were all heads, and they would justify to themselves somehow that the probability that the next one's tails is either higher or lower than 1/2. But it's 1/2 if the coin is fair. Okay. Knowing this can save you potentially a lot of money. Right. So that was the first one. Not particularly challenging. This was a little difficult putting this together, but this one, easy question. All right, challenge 2. Okay, challenge 2. A flush is a set of 5 cards that are all the same suit. So in many different card games, you get dealt 5 cards. And a flush is when they are all the same suit. So if you have 5 clubs, 5 spades, 5 hearts, 5 diamonds. Okay, that is a flush. If you were to draw 5 cards from a complete deck, what is the probability that you get a flush from those 5 cards? So we want to know the probability of getting flush. So Again, this is going to involve 5 different events, pulling 5 different cards. Let's think of them one at a time. For the first card you draw from this deck, 52 cards in the deck, how many of them will get you closer to getting a flush? How many of the 52 cards in this deck will allow you to end up at a flush? Well, any club, any diamond, any heart, or any spade will get you towards a flush. So for example, let's say I got rid of all the things that aren't really cards. Let's say I draw this, the 7 of hearts. Okay? If I draw this card first, I can get a flush by getting 4 more hearts. If instead I were to draw another heart, let's not do that. The ace of spades, okay? If this were the first card I drew, I could get a flush by getting 4 more spades. So really, any card in this deck, if it's the first card, will allow me to get a flush. So the first event, the probability that I get a flush, closer to a flush on that first card, is really any card in the deck will allow me to do that. 52 out of 52. But then let's say I drew the 2 of spades. Okay, that's the first card I drew. I put it off to the side. It's in my hand now. How many of the cards remaining in this deck will allow me to continue on towards my flush? There are 51 cards left in here. The 2 of spades is off to the side. 51 cards left. How many spades are left in here? Just 12. Okay, so you take another spade. I'm not going to do it at random this time. We're going to actually make sure that we get 6 of spades as the second card. So it also goes in my hand. I've now got 2 spades in my hand. 2 and the 6, they're here. I want to continue drawing cards to get a flush, all spades. So the third card, what's the probability the third card gets me closer to my flush? Should be 11 out of 50. We can keep going this way for the 4th and 5th cards. It follows the same pattern. That's a 4. Oops. All right. And so what we would do with all these, we would multiply all those together. If you were to do this on a calculator, the probability of getting a flush is approximately 0.2%. Not super high, only about 1 every 500 hands or so. That is how you would do that. So taking a complicated probability that involves 5 separate events, breaking it down into 1 at a time, will help you attain that. Challenge 3. Alright, consider the sum of values of 2 dice. So, from earlier in the video, we did that simulation. We're talking about that C column, where we added the 2 values of the dice together. What is the probability of rolling a sum of exactly 2? Okay. We simulated that back in that part of the video, but what is the true probability of getting a total of 2? That might involve making a list or a table of all the possibilities when you roll 2 dice. So let's go ahead and do that. I'm going to do it this way. 1 through 6. Then you've got the second die here. That's going to be the rows. We can go 1, 2, 3, 4, 5, or 6 that way. And what we're going to do is we're going to fill out the rest of this table with the sum of the row and the column. So 1 plus 1 gives us 2. Might help if I do this. 1 plus 1 gives us 2. 1 plus 2 is 3. 1 plus 3 is 4. So on and so forth. 1 plus 6 is 7. We can do that for the rest of the rows as well. You'll find pretty shortly there is a pattern here. Oop, that is not 9, not even close. I got a little carried away. I just wanted to keep going from 8. That's not how it works. So, these are the sums that you get by rolling whatever number column you're in and whatever number row you're in, from 2 all the way up to 12. So, what is the probability of rolling a sum of exactly 2? Well, how many ways can we get 2? Just this one. Out of how many possibilities total? Well, there's 6 rows and 6 columns, so there are 36 numbers in here. So it's 1 in 36. Probability of rolling a 2, or the sum of 2, is 1 in 36. What is the probability of exactly 7? Well, there are 6 different ways of getting 7. We said this in the simulation part of the video, but now we're actually seeing why that's the case. You can get a 1 and a 6, 2 and 5, 3 and 4, 4 and 3, 5 and 2, or 6 and 1 to get 7. So the probability of a sum of 7 is 6 out of 36. Okay. So let's move on here with this question. If someone were to give you $3 if you rolled a sum of 2 first, but you would have to give them $1 if you rolled a sum of 7 first, would you agree? So you would win $3 if you rolled the 2 first, but you would have to pay $1 if you rolled a 7 first. It's much more likely to roll the 7 first, right? Because it's 6 out of 36. But, is it worth winning $3 to pay 1? I don't know. Well, I know. Is it or not? What if they gave you $10 to do this rather than rolling the 7? Would that then be worth it? I wonder how much they'd have to pay you for these to even out in the long run if you were to play over and over and over again. This truly is a challenge question. There are lots of different ways to solve this. I will show one way and talk about another way. So we could set this up as an equation. We could find what's called the expected value, and we have not discussed this yet. I don't expect you to have known this. Okay. The expected value, you would take, well, let's see here. If you were to play this game 7 times, you would expect this to happen 6 times for every 1 time that happened, right? Because this is 6 times as likely. So 1/7 of the time, you're going to win some amount of money. This is what we're trying to find. The other 6/7 of the time, you're going to pay $1. And we want that to even out in the long run. So that equals 0. We just need to solve this for x. So this is going to be x over 7 minus 6 over 7 equals 0. That's x minus 6 over 7 equals 0. Multiply both sides by 7. That means x minus 6 is 0. Add 6 to both sides. The amount that you would need to get paid for it to break even is $6. So if they're willing to pay you $3, you shouldn't play. But if they're offering 10, you should. Anything over 6, you're going to profit on average. Okay. Another way to do that without setting up this equation here, if this happens 6 times more often than this, then they would need to pay you 6 times more than you're paying now. And since you're paying $1, they should be paying 6. Okay. So, those are just some challenge problems. I hope you enjoyed going through those if you stuck around. There are lots of different challenging questions that we can ask based on the concepts in this section. This is just a little taste. If this kind of stuff interests you, I would encourage you to pursue further studies in statistics. It gets a lot more interesting than this, a lot more fun. And if this does excite you, then seek it out. It's a cool world to live in. Okay? But for this video, that's it. Take a look at that remind message for your homework for section 4.1. It will be due next Wednesday. And we will see you again tomorrow with the first video for chapter 4, section 2. Have a good day.